Hi guys, so today we're going to revisit systems, except this time instead of looking at systems with lines or looking at those three variable systems with planes, we're going to look at the last type of system we haven't looked at, which is systems that involve lines and parabolas, or parabolas and parabolas, and then also looking at systems with circles as well. So really getting into some quadratic equations when it comes to solving these systems. So to start, we're just going to look visually at some of the possible things that can happen here. Okay, so we'll start with a line and a well, I shouldn't say quadratic, a line and a parabola. And we'll look at some of those cases. So one thing that's possible, if you have a line and a parabola, is you could have your parabola and your line not intersect and have no solutions. Okay, just like you could have with two lines. You also could have that intersect in one place and have one solution. Now, if you have a case like this where it just intersects in one place, that place where it intersects is the line where that line is tangent to that parabola. So you might remember that terminology from last year in geometry. That's going to be an important one going forward for you guys. All right, you also could have your parabola and your line intersect in two places potentially. So that's something that we haven't seen so far, the possibility of two distinct solutions. All right, let's look at if you have two parabolas. So I could have a parabola and a parabola not touch and have no solutions. They could touch in one place and have one solution. They could touch in two places and have two solutions. So again, it is possible to have two distinct solutions. Well, it's also possible, though, if we have a vertical and a horizontal parabola, we can now have three solutions, or even four solutions. You'll also see some examples today involving circles. If you don't remember circles, something in the form of this. Okay, that's kind of an example of a circle. You'll see, you won't have to graph them today, but we'll look at it really just kind of get some extra quadratic practice in solving. But again, visually kind of what can happen here, whether it's a line or a parabola, a circle and a line, you could have one intersection at the point of tangency. You could have two intersections. That would be referred to as the secant line. Again, remember you learned about that back in geometry. Tangent and secant will come back up for you guys later on in life. You could have that circle and the parabola touch in three places. And you could have a circle and a parabola touch in four places. So really a lot of different options here today. You could have no solutions all the way up to four possible solutions. So to start, let's just look at a couple of these by graphing. All right, so this is again just really graphing review. To graph this one, you could either complete the square to write it in vertex form, or you could do negative b over 2a to get the vertex. I think on the last video I did vertex form by completing the square, so let's do negative b over 2a this time. So negative b over 2a would mean that the y or x coordinate of our vertex is 1. Plug 1 in, 1 squared minus 2 minus 1. Would be a negative 2. So your vertex here is 1, negative 2. This graph has not been stretched or compressed or reflected in any way, so it's going to follow the same parent function pattern from this point. So right 1 up 1, right 2 up 4, right 3 up 9. And let me try and get this one a little bit more accurate so I make sure I can get that intersection point clear. There we go. Again, those points are not points in the graph, it's saying how we're moving from the vertex. All right, and the next one is a line. Okay, that line has a y-intercept of negative 1 and a slope of negative 2. And that's why I try to get it close so you could see that it's only intersecting in that one spot. So that line is tangent to that parabola in that one place. So 0, negative 1 is my solution. All right, looking at the next one, we've got two parabolas to graph. This first one, the vertex is 1, 1. It's been vertically, or it's been compressed by 1/2. So again, typically that parent function pattern looks something like this, but because it's been compressed, so from the vertex, that's how we're moving. So right 1 down 1/2, right 2 down 2, right 4 down 8, will be barely on that graph. I should have gone over, whoops, one more. Not a very accurate picture, sorry about that. There we go, that's a little better. Okay, then that other graph still has a vertex of 1, 1. And I don't know why I made that graph. I'm sorry, guys. I'm looking at the second one and combining the second picture with the first one. So on this graph here, I'm going right 1 up a half, right 2 up 2, right 3 up 4.5. I think I was just trying to force that one to fit on my graph. There we go. There's a little bit more of an accurate picture. Sorry about that. All right, then on this next one, there we go. Still has a vertex of 1, 1, so you guys can obviously see that intersection point. But let's just graph it to go ahead and get that practice in. Okay, it's been reflected. And it's been stretched. So from that vertex, right 1 down 2, right 2 down 8. All right. So now that these are graphed, we can see that vertex is located at 1, 1. And that's the point of intersection. All right, so now we'll just do a little bit more graphing review. We'll go ahead and graph a system of inequalities. So this is combining what we did last class and just getting some good extra graphing practice in. So these are all in vertex form, so they should be a little bit easier to graph. So in that first one, okay, that vertex is 1, negative 3. It's been compressed by 1/2. So from that vertex, okay, that's my normal pattern. I'm compressing it by 1/2. So I'm going to go over 1 up a half, over 2 up 2, over 3 up 4.5, and over 4 up 8. All right, this is going to be a dotted line because it's not or equal to. And then shading, it's y is greater, so I'm going to shade above the vertex. Above the vertex, in this case, is going to be inside that parabola. All right, let's look at the next one. The next one has a vertex of 2, 4. Again, that's the normal parent function pattern, reflected and stretched. Okay, obviously that's going to be way off my graph. This one is also a dotted line. Whoops, too far over on that one. There we go. Y is less than, I'm shading below the vertex. The below the vertex is also inside that parabola. So the overlap of the shading here is going to be what is inside both parabolas, which is this region right here. All right, looking at the next one, we'll start with this first one. We'll graph that vertex, negative 3, 2. It's been compressed by a factor of 1/4 and reflected. So from that vertex, so I'm just going to put a couple points on here. I'm just going to go right 2 down 1. And that's really going to be enough because I'm going to run out of space. This is going to be a solid line. And then I'm shading above the vertex, which is outside the parabola. So it would be all that part. All right, looking at the next one, has a vertex of negative 1, negative 2. No transformations from the parent function. So right 1 up 1, right 2 up 4. That one's going to be a dotted line. I'm shading above that graph. Okay, so above that graph is going to be, in this case, inside the parabola. So the overlap of these two is going to be what's outside the blue parabola and inside the purple. So that's going to be this region in here. Something else it said to do is to state two possible solutions. Again, that's any point that falls within that shaded region. So like on this one, you got a lot of options here. 0, 2 is a possible answer. -1, 5 is a possible answer. On this one over here, you've got 2, 0 as a possible answer. 2, 1 as a possible answer. Lots of different possibilities as long as it falls in that shaded region. All right, so what we're going to do now is we're just going to solve these algebraically. And honestly, guys, this is really just more practice on solving quadratics. The biggest thing I will tell you to be cautious about when it comes to solving these, if you use elimination, you need to be careful. What you do not want to do is try to eliminate the x squared term. Because when you eliminate a variable, you're trying to eliminate that variable completely. If you eliminate the squared term, you still have an x and a y. And then you're only going to have one equation to be able to solve it, which isn't possible. So if you do elimination, you can only eliminate the variable that does not have a squared variable as well. So in this case, if I want to do elimination for y, that's okay because there are no other y's. What I can't do, though, is say, hey, let me multiply everything by -2, and then I'll eliminate the squared term. That's not going to work because then you're going to have one equation and two variables. So be cautious when using with elimination. I will say I personally feel like on a lot of these, substitution is just an easier process, but that's just me. This first one, though, we'll go ahead and do elimination because, again, if we eliminate y, that's okay because that's all of that variable. That variable is completely eliminated at that point. All right, so that gives me this equation that's left over. That equation is quadratic. It's not going to factor, so we can try completing the square or quadratic formula. And you'll notice inside this square root, that discriminant is going to give you a negative value. If we're giving the square root of negative, that's not going to be any real solutions. And again, because we're talking about this practically, when we talk about systems, we're talking about where they intersect. If I'm getting a negative answer here, it means those two graphs don't intersect. Okay, these are parabolas. This is a case something like this. Okay, or I mean many other options the way it looks, but the point is that those graphs will not intersect. So there's no real solution. You do not need to find imaginary solutions on this, just like you didn't need to when you were doing those inequalities. All right, on this next one, again, either elimination or substitution. I'll go ahead and do substitution because it's set up pretty easily for that. And you'll notice, again, these really aren't that difficult. It's really just extra practice on solving quadratics. Okay, so set that equal to 0. This is going to factor. Only one possible x value, which means there's only going to be, well, sorry, it doesn't necessarily mean that, but we only have one possible x value here. Okay, so I'm going to take that x value, and I'm going to plug that in to either equation. I'll go ahead and do the bottom one because that's a little bit easier. So my solution here is -2, 0. If you wanted to write your answer as x equals -2 and y equals 0 and box that, that's okay. Just be careful you make it clear that which y is associated with which x. Because going further in these, when you have multiple solutions, those x's and y's do need to be paired together in your solution in order to be clear. You can't just say these are the x's and these are the y's. You have to know which x goes with which y. All right, if you're feeling pretty comfortable, pause the video, try these ones on your own. All right, I'm going to go ahead and do substitution. So I'm going to take, this one's already solved for y, so I'm going to plug it in. Now, the reason I did this one in particular is to make sure you guys are careful. When you subtract, you are subtracting that entire function. So this becomes x minus x squared minus x plus 1. So x minus x is going to cancel out. I will go ahead and get negative x squared is equal to -5, which means that x squared is equal to 5, which means that x is equal to plus or minus the square root of 5. So now I have two possible answers for x, positive square root of 5 and negative square root of 5. Each of those x's is going to have a y coordinate associated with it. So I'm going to take that x and I'm going to plug it in to either of those equations. Doesn't matter, it's up to you. I'll go ahead and use the top equation, but I'm going to go ahead and just solve that top equation for what y is to make it a little bit easier. So that top equation, that's x plus 4 is equal to y. All right, which means if x equals square root of 5, the y value that goes with it is the square root of 5 plus 4. Or more frequently, you'll see that written as 4 plus the square root of 5. There's nothing wrong with writing it the other way, but personally I like writing it this way better. That way it's very clear that the 4 is not under the square root and you don't get confused. So that is one solution. Your other solution, when x equals negative 5, then y is going to equal 4 minus the square root of 5. So those are two distinct solutions. You can either write them that way, or you can write them as an ordered pair. It's up to you. But what you can't do is just write, here's all the x's and here's all the y's. You need to make it clear which x goes with which y. All right, on this one, again, I'll do substitution. Take this, I'll plug it in. And really, you just have a big quadratic equation. I'll set it equal to 0. This can factor. I get two possible values for x. And again, remember, each of those x values is going to have its own y value associated with it. So to figure out what that is, plug it into either equation. So y equals, I'll use the bottom one, 2 times 5 squared minus 5 plus 9. That gives me the y coordinate of, let's see, that's 25, 50, 54. So x equals 5, y equals 54 is one solution. All right, the other one, again, plug it in, negative 2. So 2 times negative 2 squared plus 2 plus 9. So that's going to be 4, 8 plus 9 plus 2 is 19. So your other solution is negative 2, 19. So two possible intersections here. All right, just a couple more. Again, very similar type problem. Up to you how you work it out. In this case, you could do elimination because you can eliminate y. Again, we don't want to try to eliminate just the x squared because that's still going to give us a variable and we're not going to be able to solve it that way. But we can go ahead and do 3x squared plus 4x, those y's cancel out, equals 0. And then hopefully you guys know this is an easy to factor and solve question. This is something you want to factor. Take out that GCF. So your two possible x values are 0 and negative 4/3. Each of those is going to have its own y value associated. So let me just rewrite this. All right, so with x equals 0, I would get y equals 2. With x equals negative 4/3, I would do negative 4/3 squared, square the top and the bottom. That's going to be a negative 16 over 9 plus 2. Get a common denominator, and that's going to end up being 2 over 9. So negative 4/3, 2/9. All right, and then the last one before the word problem. This one is a circle, okay? You know that because you have an x squared and a y squared. And again, we don't need to worry about graphing this. If you want to graph it, you can. Just as a reminder, this would have a center of 0, 0. The radius would be the square root of 10. That's what that graph would look like. But let's just go ahead and solve it algebraically. All right, substitution is going to be easiest and kind of your only option here. Take this y, plug it in. So negative 3x plus 10 squared equals 10. Remember, when you square this, you are not squaring the individual terms. You have to square the entire binomial. Negative 3x plus 10 times negative 3x plus 10 and FOIL it out. So that's going to give you 9x squared minus 60x plus 100. And now just combine like terms. Set it equal to 0. And before I try to factor this, I'm going to reduce it. Okay, this is an equation, so I can divide everything by 10. And now it's pretty easy to factor. Perfect square trinomial. Only one possible answer for x. take that x value, plug it into one of your equations to get your y value. So your solution here is 3, 1. All right, last one, just a word problem. So just an example of some things that you can do with these systems when you're dealing with some nonlinear stuff. So it says the area of a rectangle is 120 inches squared and the perimeter is 46 inches. We want to find the dimensions, so the length and the width. Okay, so if the area is 120, that means the length times the width is 120. And we'll just go ahead and use x and y because we're used to that. If the perimeter is 46, 2x plus 2y is equal to 46. Now this equation actually is not quadratic, but the reason we're including it here is because you're going to need a quadratic equation to solve this. So you can solve for either x or y in this one, kind of up to you. I'll go ahead and just get x by itself. So we'll do substitution. So x is equal to 120 over y, and then I'm going to go ahead and plug that in. So this is 2 times 120 over y plus 2y equals 46. So that's going to give me 240 over y plus 2y equals 46. And although it may not look like it right now, this is a quadratic equation, because what I can do, let's go ahead and multiply everything here by y. That's going to give me 240 plus 2y squared equals 46y. And this is now a quadratic equation. All right, to make it a little bit easier to work with, I'll divide everything by 2. Oops, forgot to divide that by 2. And let me rearrange it. There we go. And this is going to factor. There are numbers that multiply to 120 that add to a negative 23. Those numbers are negative 8 and negative 15. So your possible answers for y are 8 and 15. And then just because both of those numbers multiply to 120, the option for x is the other one. So it's clear here, it doesn't matter which one's length and which one's width, your dimensions are going to be 8 by 15 or 15 by 8. All right, so that's it for systems. Again, not too much new here, really just kind of combining two things we've done so far this year together. And again, you notice a pattern here. We're getting extra practice in solving these quadratics. Solving quadratics, guys, it's really important. It's something you got to be able to do pretty quickly and easily. Figuring out, hey, does it factor? If it factors, go ahead and getting that done.